Hello, I'm Dmitry Paramonov, and thank you for choosing to watch my video on why the rate of interactive codes is bounded away from 1. Before I begin, I'd just like to thank my co-authors Klim, Efremenko, Gillat, and Raghuvansh, Saxena. So, let's talk about interactive codes, but before talking about interactive codes, let's talk about regular error-correcting codes. Now, as is well known in the literature, suppose you have two parties, Alice and Bob, and suppose that Alice wants to send a message to Bob. Now, she can just send her message as is, but that breaks down in the presence of errors. If the channel randomly flips each bit with probability epsilon, then this communication will likely fail and Bob will not be able to properly recover the message. So in order to fix this, we have error-correcting codes. You append additional bits, you add redundancy, you encode all your information and send that across in order to make the message resilient to errors. These are well studied in the literature. There are many Hamming codes, linear codes. There's a ton of them out there. However, error-correcting codes come at a price. In order to make an error-correcting code, you need to add redundant bits, and this redundancy costs space. You require additional rounds of communication in order to deal with these additional bits. So this leads to the notion of the rate. The rate of an error-correcting code is simply a ratio of the length of the message you want to communicate divided by the length of the error-correcting code. Now, the bigger this value is, the closer it gets to 1, the better. It means you're using fewer and fewer redundant bits. And way back in the 40s, Shannon actually showed that the rate is bounded by a function of the error rate. So if you have errors occurring with probability epsilon, then the rate is bounded in terms of the entropy of epsilon. But still, as the error probability goes to 0, the rate goes to 1, and things are nice. However, in practice, our communication is usually much more complicated. In practice, we often can have communication go both ways. First Alice speaks, then Bob speaks, and Alice speaks. We represent this by an interactive protocol. Both parties can communicate according to some fixed schedule. We will denote the schedule by a string sigma consisting of A's and B's. So for example, here we have one potential such sigma, and we can easily think of the communication involved here. So first Alice might send a message to Bob of 0, then Alice will send a message of 1, then Bob will respond, then Alice will respond, then Bob will respond, and so on. So either way, we can have a protocol where now both parties get to speak according to some schedule they agreed upon beforehand. However, there is a catch, which is in interactive coding, things are even more vulnerable to corruptions than before. If one bit is flipped, then whatever Bob says might have depended on this bit, and his own bit will also be incorrect. This in turn will make the next bit that Alice says probably incorrect, which will make the next bit Bob says probably incorrect, and the entire protocol can break down from just one single error. So, just as error-correcting codes are used to make regular communication resilient to errors, interactive coding is used to make protocols error resilient. You take a protocol and you add additional rounds of communication to detect errors, to verify communication, to correct things, and so on and so forth. And just as before, we get a rate. If you have an interactive protocol and you have a way of making it error resilient, the rate is then the length of the original protocol divided by the length of the error resilient protocol. Once again, the bigger this number, the closer to 1, the better, because it means you're being more and more efficient with your bits. This leads to a very natural question, which is, how good can we get the rate? Back in the 90s, Schulman actually demonstrated constant rate codes, a way of converting any protocol into an error-resilient one with only constant blowup. This already gives us a constant lower bound on interactive codes, which is promising, but the question now becomes, can we do better, and how much better can we do? Well, in 2013, Cole and Ross published a paper which seemingly answered this question. They showed that the rate of interactive codes, when you have error probability epsilon in any given message, is 1 minus big O of square root of entropy of epsilon. And this is a very promising result. First of all, as the error probability goes to 0, the rate approaches 1, which is very desirable. You have fewer and fewer wasted bits. Second, they actually proved a matching upper bound, showing that this was in fact optimal. So, this seemed to be a very good result, but there is a catch. They proved that this rate applies to interactive codes for alternating protocols. So, if your protocol is of the form Alice speaks, Bob speaks, Alice speaks, Bob speaks, and so on, then you get this rate. However, it was still open whether or not this is true for general, arbitrary orders of speaking. After all, while any protocol can be made alternating, it does so at a blow-up of 2. You replace every single round with 2, an Alice and a Bob round. And as a result, now your rate will not approach 1, it will approach a half, which is significantly less desirable. And so the question was, can you still reach rates approaching 1 even for non-alternating protocols? And in 2014, in a follow-up paper, Hopler conjectured that this was false, that the rate of interactive codes is bounded away from 1, independent of epsilon. Even as epsilon approached 0, your rate would still not approach 1. And today we are proud to announce that we have successfully proven this result. In this paper, we will proceed to demonstrate exactly this. Before getting to our proof, however, I want to mention that we actually prove a stronger result. Rather than proving that the rate is bounded away from 1 in the standard noise model, we actually proved for a significantly more lenient noise model, one that is significantly more forgiving on the players. Then, the rate, because this model will be able to simulate any protocol in the standard noise model, as it is able to simulate the random flips, therefore proving an upper bound on the rate in this model also proves an upper bound on the rate in the standard model. However, this model will be significantly easier to analyze. So, let's discuss this lenient noise model, which I'm calling the very lenient noise model. And the very lenient noise model has 4 main parts to it. So the first is erasures. Rather than messages being flipped with some probability epsilon, they're actually erased. So on the right-hand side, we have an example of a communication with Alice's messages going from left to right, Bob's going from right to left, and we can see what all the players receive even if errors occur. So we can see that here, that if an error occurs, rather than receiving a flipped bit or something, you just receive a question mark. So you know that an error occurs, but you don't know what message was sent. The second thing we give them is feedback. If an erasure occurs, the sender is also made aware. So if an error ever happens, both players immediately know that an error has occurred and that they should just ignore this round and continue onwards. So this is already very good, as this allows us to get rid of having to do error detection. But it turns out we can actually make this model even more lenient, which brings us to step 3, which is that we have only 1 error. We'll choose a uniformly random round, and that's the round in which the error will occur in, so this round will just be erased, and both parties will know it, and they'll have the same transcript at all times. But further than that, we actually give the parties one more thing, which is we give them foreknowledge. So at the start of the protocol, after they've locked in the order they are speaking, so after they've decided who's speaking in what round, they are told such and such round will be erased. And this gives the parties a huge amount of leeway, because they basically get to run a noiseless protocol ignoring the round that the erasure will be happening in. And they can run a completely different noiseless protocol for every round, for every possible round the erasure might occur in. The only catch is, when running this noiseless simulation, they might not quite be running it with the order of speaking that they requested, because one round will be deleted. But as it turns out, this very lenient noise model is still enough to prove that the rate is bounded away from 1. So, with that in mind, let's talk about how we actually go about proving our result. So, we prove it using 3 separate steps. The first step is noiseless simulation. As mentioned before, in the very lenient noise model, a protocol is basically just a collection of noiseless protocols with very similar orders of speaking. So we should probably first analyze when we can solve protocols in a noiseless setting. And in particular, we look at, suppose we have a protocol with order of speaking sigma, when can we simulate it with a protocol with order of speaking sigma prime? And the answer turns out to be relatively straightforward. You can simulate a protocol with order of speaking sigma with a protocol with order of speaking sigma prime, only if sigma prime is a supersequence of sigma. We will proceed to show this in more detail later on. But given this, we actually can move on to step 2, which is simulation in the very lenient noise model. Now remember, in a very lenient noise model, a protocol is just a collection of noiseless protocols with one of the rounds deleted. And so as it turns out, you can simulate a protocol with order speaking sigma using a protocol with order speaking sigma prime in the very lenient noise model only if sigma prime is a strong supersequence of sigma. Now, what does it mean for sigma prime to be a strong supersequence of sigma? Well, that means that even if you delete any one coordinate of sigma prime, it is still a supersequence of sigma. Now, step 2 follows almost directly from step 1 and the definition of strong supersequences, but we'll show that in more detail later on. However, with step 2 now proven, all that remains to show now is step 3, which is that strong supersequences are hard. That there exists some sigma, such that all sigma prime, which are a strong supersequence of sigma, are at least a constant factor longer than that sigma. And we claim that this completes the proof. Why? Well, simply take sigma as given by step 3. Now, consider any protocol with order of speaking sigma. You can easily solve it in the noiseless setting using order of speaking sigma, as described. However, if you want to then have error-resilient simulation of that protocol in the very lenient noise model, you will require a strong supersequence of that sigma. But by step 3, all strong supersequences are at least a constant factor longer than it. Thus, all protocols which simulate that protocol in the very lenient noise model are at least a constant factor longer, which therefore proves a bound on the rate away from 1. And that sort of concludes the proof. So, with that in mind, let's actually show these steps in more detail. So to begin with, let's look at step 1. And once again, what we want to show is that any protocol with order of speaking sigma can be simulated by a protocol with order of speaking sigma prime, only if sigma prime is a supersequence of sigma. So how are we going to show this? Well, for this we will consider a problem which is complete for protocols with order of speaking sigma. If we have a problem which can be easily solved by protocols with order of speaking sigma, which can in fact represent any protocol with order of speaking sigma as an instance of itself, and if we can then show that this problem can only be solved by protocols with order of speaking sigma prime, only if sigma prime is a supersequence of sigma, then we are done. So what we need is such a complete problem. And to do this, we'll be using the very standard pointer chasing with order sigma problem. Here, parameterized by some sigma, both players are given a complete tree of depth equal to the length of this order of speaking, with one layer per coordinate of sigma, which as can be demonstrated on the right. Now, this is parameterized. Both players know this tree and know this assignment ahead of time. As inputs, however, each player receives a correct child for every node in their layers. So here we see Alice's view. For all the vertices in her layers, there's one correct outgoing edge, and she knows nothing about Bob's layers. And vice versa, Bob knows the correct children for his layers, but doesn't know Alice's. However, when we put them together, we see something very interesting, which is that if you start at the root, and you only go down these correct edges, there is a unique path which takes you to a leaf. And that is the goal of this problem. The players want to output this leaf, which can be found by repeatedly taking this correct child, starting at the root. Now, this problem is easily solved using order of speaking sigma. Why? Well, first the first player says which of their children to go to, using one round of communication. Then the next player says which of the next children to go to, one round of communication. Then the next child using one round of communication, and so on. So solving this with order of speaking sigma is easy. Furthermore, this problem is actually complete for all protocols with order of speaking sigma. Why? Well, any protocol with order of speaking sigma can be represented as an instance of pointer chasing. Simply, a protocol is a collection of functions saying what to say for any given transcript so far. This can easily be represented using a pointer chasing instance just by saying, at this node, which represents the transcript so far, which one of the children is the correct one. So therefore, any protocol with order of speaking sigma can be turned into an instance of pointer chasing. Therefore, what we now want to show is that you can solve pointer chasing with order sigma using a protocol with order of speaking sigma prime, only if sigma prime is a supersequence of sigma. If we show this, then we've shown step 1. So, to show this, let's actually first look at a very simple example. Let's take a look at the order of speaking AB. So, on the previous slide, I drew the tree as a binary tree, but in actuality, our proof uses a large alphabet, so it would look closer to what we have here on the right. And what we claim is that you can't solve pointer chasing with this sigma using order of speaking B, A. So in other words, if Bob speaks before Alice does, no matter how many messages he gets to send, you can't solve pointer chasing with order of sigma. Why is this the case? Well, simply consider what Bob sees until Alice first speaks. Until Alice speaks, Bob has no idea which of his many nodes is the correct one. He has no way of guessing this information, so he will probably be able to, communicate information about some of the nodes, or maybe some, correlations among them. But because we have a large alphabet, then no matter how many messages he gets to send, he can't actually communicate anything meaningful. Until Alice speaks, Bob's messages are useless. But once Alice speaks, Bob no longer gets to speak, so he can't, update Alice on what the correct node is. So, therefore, until you know what you're supposed to be talking about, you have too many options to communicate what you need to say. In the general setting, we can then use this argument further. Consider a general sigma and sigma prime with an example here on the side. Now, suppose you're trying to solve pointer chasing with order sigma using a protocol with order speaking sigma prime. We now get something very interesting, similar to what we had before, which is that until you know which node you're supposed to be at in a given layer, you can't communicate any meaningful information about the correct node in that layer. Just as before, until you know where you're at, you can't communicate meaningfully. However, it gets a bit more difficult to figure out when you can know where you're at in the general case. So, in order to analyze this, what we do is we'll consider an embedding. Simply match each coordinate of sigma to the earliest coordinate it can match to in sigma prime. So we match the first A to the first A, then the second A to the first A after that, the first B to the first B after that, and so on and so forth. But furthermore, we don't just match them, but we actually want to look at blocks. We want to take a look at blocks where just one player speaks in sigma continuously. So a bunch of consecutive Alices, then a bunch of consecutive Bobs, then a bunch of consecutive Alices, and so on, and consider what these blocks map onto. In particular, consider the last point in all of these blocks. So we claim that until you reach the end of one of these blocks, you can't communicate any meaningful information about nodes in any of the later layers. So until we get to this A, anything in these layers of pointer chasing with order sigma you can't communicate any useful information. Until we get to this node, you can't communicate any useful information here and down. So, how do we go about showing this? Well, we prove this using a relatively simple inductive argument. Consider any one of these blocks. Until the end of the previous block, the person who owns this block couldn't have started talking about this. So therefore, because no information about this block could be conveyed, you don't know where you're supposed to be at in any later layer. So therefore, until the end of the previous block, by induction, you don't know anything about this layer. Then, because this block has two elements, you need at least two messages in this block in order to know where you're at. While you might be able to send information about the latter layers and earlier messages, until you know all of the layers along the way, you can't actually get anything meaningful. So until you reach this part, until you reach the end of the embedding of this block, you can't make any progress. And sort of this argument proceeds by induction. Now, there are a couple more technical details in the proof. You need to basically argue that it's impossible to guess where you're at. You need to argue that you can't communicate information about your entire input or send information about correlations in any meaningful way. Our full proof goes into all these details, but we omit that information for this video. And with this general approach, once you have this lemma, what you can basically argue is that if sigma prime is not a supersequence of sigma, then the last element of sigma will not embed into sigma prime. It'll sort of go beyond the end of sigma prime. So by the time you get to the end of sigma prime, you haven't gotten to the end of sigma, so you can't output information about the last layer, and so therefore you can't solve pointer chasing with order sigma. And that basically proves the result we want for step 1. Step 2 then follows almost by definition from step 1. Recall that a protocol in the very lenient noise model is just a collection of protocols with similar orders of speaking, depending on which round was erased. And so, if sigma prime is a strong supersequence of sigma, then deleting any coordinate of it still results in a supersequence of sigma, so you can just simulate it by the results of step 1. On the other hand, if it's not a strong supersequence of sigma, then deleting any coordinate will result in something that's not a supersequence of sigma. So by step 1, that noiseless simulation doesn't work, and if it's not a strong supersequence with high probability, it won't result in a supersequence, and so with high probability, you can't simulate it. Step 2 follows almost directly by definition from step 1. As such, it just suffices to prove step 3. Now, as a reminder, what we want to show is that there exists some sigma such that all sigma prime, which are a strong supersequence of sigma, are at least a constant factor longer than it. In order to show this, let's actually first formalize this a bit more. What we really want to show is that for all t, for all lengths t, there exists some sigma of length t, such that any sigma prime of length at most 1 plus delta times t is not a strong supersequence of sigma. This will, by the converse of this, will automatically prove that all strong supersequences are at least a constant factor longer than it. So, how do we go about showing this? Well, we use a probabilistic argument. We show that a uniformly random sigma satisfies this condition with non-zero probability. This just directly proves that there must exist some sigma and will be done. However, even proving this is a bit difficult, so we'll actually break it down further. Now, in order to show this, recall that we're dealing with strong supersequences. And an interesting fact is that any strong supersequence is also a supersequence just from simple arguments. So what we actually do is we start asking ourselves the question, in what way is sigma prime a supersequence of sigma? In particular, we will look at things we call patterns. A pattern is a string of length 1 plus delta t, which consists of a's, b's, and blanks, such that exactly t of the symbols are blank. Here is one example row. Now, why is this interesting? Well, we can now take a sigma consisting of t's, a's, and b's, and we can insert it into row to get some sigma prime. Now, recall that if any sigma prime is a supersequence of sigma, then it'll be a supersequence via one of these patterns, so to speak. So what we actually do is we will apply a probabilistic argument to patterns as well. We will show that given a uniformly random sigma and a uniformly random row, the sigma prime that you get by inserting sigma into row is not a strong supersequence of sigma, except with exponentially small probability. Why is this useful? Because then what we can do is we can simply take a union bound over all possible row and show that all such sigma primes are not a strong supersequence of sigma, except with some probability less than 1, which concludes the proof that we want. So how do we go about showing this? Well, the first thing we should do is we should take a look at a very simple example. Consider the pattern row, which consists of t blanks. Now, clearly any sigma prime you get this way won't be a strong supersequence because it'll be of the same length as sigma. So let's ask ourselves a simpler question. If we get sigma prime using this pattern, what is the longest prefix of sigma such that sigma prime is still a strong supersequence of it? So now we're not looking at sigma into sigma prime, we're looking at just a prefix of sigma. And in order to answer this, we're going to look at a notion, we're going to introduce a notion called lag. Now, what is lag? Well, consider the following. Suppose that we have sigma, and our row, and suppose that the first coordinate of our sigma prime is deleted. Then, the first coordinate of sigma will have to be embedded in one of the later terms. Maybe it gets embedded into the one immediately after it, or maybe the one after that. But either way, we can get a notion of lag. Lag is the difference between the coordinate that coordinate I is mapped onto minus the initial coordinate I. And what we get is very interesting, which is that, like, if the second term is A, then the lag just becomes 1. Or, on the other hand, if the first one is B and the next one is A, then the lag becomes 2, and so on and so forth. And because sigma is uniformly random, we actually get that it becomes 1 with probability a half, 2 with a probability a quarter, and so on and so forth. But something very interesting happens when we take a look at the next term, say the B, because the B might map onto the next one, in which case the lag will remain the same. Or it might map onto the one after that with probability a quarter, in which case the lag will increase by 1. And you can actually analyze this and see that for every single one of these coordinates I, in expectation, the lag increases by 1. So as we step along sigma, the lag keeps increasing and increasing and increasing by 1 each time in expectation. But that's very interesting, because that means that, except with probability exponentially small, by the time we get to 0.9 t of the coordinates of sigma, the lag already exceeds 0.1 t. So by the time we get through the first 90% of sigma, we're already past the end of rho. The lag means we're just going beyond the end of it. And so therefore, we get that the longest prefix of sigma, for which sigma prime is a strong supersequence, is going to be about 90% of sigma, which is how our analysis is going to proceed. It's going to be looking at this lag and claiming that the lag is very big by the end, to the point that we run out of coordinates. However, in the general case, things aren't as simple, because we're not dealing with a trivial pattern. We're dealing with a pattern which might include non-blank coordinates. And these non-blank coordinates are a problem, because a non-blank coordinate can actually decrease lag. For example, consider the simple pattern rho listed here, with a blank, a, b, and then a bunch of blanks, and consider trying to embed sigma into that with the first blank deleted. Well, if the first coordinate is an a, it'll just map to the first a, and then the rest of the elements of sigma will just map to the corresponding blanks, and if the first coordinate is a b, it'll map to the first b, and the rest of the coordinates will simply map to the corresponding blanks. In either case, the lag will become 0. And if we have a lag of 0, we don't have our result. However, we do have one advantage here, which is that a non-blank coordinate can decrease the lag, but it can only decrease the lag by 1. And at the same time, meanwhile, we also have that as long as the lag isn't 0, when we get to one of our blanks, that blank coordinate still increases the lag by 1 in expectation. And so what we actually get is that as long as the lag never hits 0, then we have t blank coordinates, which will increase the lag by 1 in expectation each, and delta t non-blank coordinates, which decrease the lag by at most 1. So in expectation, our increase in lag is still omega t. So by the time we get near the end of sigma, we're already past the end of sigma prime, and we have the result we want. So this is how we prove it. Now, there are a couple of catches here. Notably, we need to prove that the lag never hits 0, which we do through a sort of recursive build-up of starting with a very small sequence, then that builds up. You need to argue that you can't have very large runs of non-blank coordinates, or rather that if you do, then the rest of the string will be convenient. But we omit these details, and you can find the details in the full paper. So, before I end this video, I just want to raise a couple of open questions. The first is whether or not you can show these bounds even with a binary alphabet. As a reminder, we're using a very large alphabet here, but we believe that the result still holds even for a binary alphabet. However, our approach directly doesn't work, and it requires some additional analysis. Another open question is whether or not these bounds hold for adaptive protocols. If the parties are allowed to change the order that they speak in based on their inputs, and even better, based on the messages that have been communicated so far, do we still get the same bounds on the rate? Whether or not this is true, we still leave open for further research. Now, finally, I just want to say thank you all for listening and for watching this video. Have a wonderful day.